In the last class, right, we talked about, well, last week we talked about history of vibration, and then we talked about a specific kind of vibrating system, which was a pendulum. We looked at the pendulum, its equation of motion. It was a second order differential equation. We solved that differential equation, that equation of motion. We found the system response from there, if you remember, which basically pretty much it tells us where the pendulum is at any given time, as long as we know, we can say where the pendulum is at any given time, as long as we know the length of the string in the pendulum and we know its initial conditions. Those are enough for us to know exactly where the pendulum is or how the pendulum responds to initial conditions, to a given initial, let me rephrase. We can exactly say where the pendulum is at any given time knowing those, as I said. Now, in this class, I want to look at a different type of vibrating system, similar in nature, you will see, but different form. And it's a very common type of vibrating system in mechanical vibrations, right? And that's spring mass system. Now, let's take a look at this system. We're going to do what we did for a pendulum, right? We are going to derive the equation of motion, and knowing the system's parameters, which in this case is mass and stiffness, we can find the system response, and we can figure out where that mass is when it's vibrating or connecting, when it's connecting to a spring and it's vibrating. We can say where that mass is at any given time, knowing the system parameters and initial conditions. Now, so let me put it this way. I apparently forgot to. Okay, spring mass system. Spring mass system. This is the most common vibrating system we're going to see in this course. Keep in mind, these are very simple vibrating systems, but very, very important, because we are going to use these systems and these concepts like natural frequency and time period I defined in the last class, to actually explain and describe much more complicated systems. You will see during the semester how do we connect the dots and how can we go from these simple systems to those very complicated, more, I would say sometimes practical things and systems. So let's divide the spring mass system into two groups. I'll say a type of spring mass system that the spring is horizontal, right? And one mass is attached to a mass is attached to one side of it. Right? So I'll go with something like this. This is the spring I show, and we talked about the springs. It's a linear spring, and the stiffness is K. And this is a mass with mass of M. And I use two small wheels here showing that there is no friction between the mass and the surface. Just those are the, that's the role of these wheels, to just show that there is no friction on the surface. You might see it without wheels and they tell you there is no friction. It's pretty much the same thing. Now let's find what is the equation of motion for this. So I do what I did for a pendulum, right? We follow the procedure in like dynamics, the way we do it in dynamics. We draw the free body diagram, we draw the kinetic diagram, and then we just compare them together and see where does that take us. So let's say I have a free body diagram here. This is the mass. What is applied to it is, well, a normal force from the surface, right, opposing the mass or the weight, mg. Now, I'm going to consider the motion to right as the direction of the motion. This is an assumption. You always have to make an assumption about which direction the system is moving. Right? In this case, I assume that it's going to the right. First thing you have to assume. So if it's going to the right, this spring is trying to pull the mass back to its equilibrium point. This is the equilibrium point. I'll talk a little bit more about the equilibrium point. So at this point, the spring is not stretched. Spring is at its undeformed length, meaning that there is no initial force in it. Once we start moving away from this equilibrium point, equilibrium position, going to the right, the spring is trying to pull the mass back to where it was. That's what the spring does. Right? So Kx, the force of the spring, it's a linear spring. And that's pretty much it on a free body diagram. Now looking at kinetic diagram, or you might have referred to it with a different name, inertial force diagram or something along that line. If we look at this mass, the only component we have is pretty much the acceleration, linear acceleration, right, going this way. Pretty much we represent that with ma. Right? And if you think about it, a in this linear motion, a is acceleration, so it's the second derivative of time. That would be mx double dot. So making these two equal, form the using the second law, right? Newton's second law, summation of forces is equal to ma. So what do you get from there? One thing I have to mention, after assuming the direction, I said x is moving to right, you assume that direction. The second thing is always in this course, always take the direction of the motion as positive. So if I assume that x is going to right, then that direction would be my positive direction. So that's the general rule. Let me just put it here. So this is the positive direction. Now looking at these, well, I'm gonna get minus kx is equal to mx double dot, and from there I'll get mx double dot plus kx is equal to 0. And this would be my equation of motion. All right, let me just put it there. This is, I represent that with EOM, equation of motion, for a spring mass system. Good. Did everyone follow that? Pretty much what we knew from dynamics. Now, the second type that I would say, well, not the second type, the second configuration of a spring mass I want to talk about is when the spring mass is in a vertical direction. And now, why is that different? Because in that case, here we saw that, well, the weight and normal force from the surface are going to be equal, so we don't even care in that about that direction. There is no motion in that direction. It's a static equilibrium in horizontal direction. Now, if I have a system like this, if I have, let me change the color. If I have a spring mass system in this form, this is a little different. Why? Because, well, at this point now I have gravity. Gravity is affecting the way this system is moving, or at least that's what we might think. Okay, we'll see how it works. Now, how do I study this one? Now, to study this one, I'm gonna follow this procedure. Assume that, follow me here. Assume that we have a spring and no mass is attached to it. So it's in undeformed shape. Right? I have the spring here. I have a spring, see the spring hopefully. It's in undeformed shape. No mass is attached to it. No mass attached to this one, it's undeformed shape. Now what I do is I'll go and add a mass to this system. And I'll let it be. Right? Now the spring is undeformed. It has some length. So that's what I did. I said, for this system, let's say I have spring, right, like this. So undeformed shape, K. Now what I did was I added a mass to it and let that force be applied to the system. Now this is the mass and this is the spring. Now what happens is that the spring is going to be stretched a little bit, right? This is where the springs, this is the first one on the left is basically where the spring is in its undeformed shape. This one is when the spring is stretched. I'll call that delta amount. Now it's standing there, not oscillating. So this is a static equilibrium. All right? Remember from static, this is a system in equilibrium and it's at rest. So I can write the equation of motion for this, or I can write the equations for this. For the static equilibrium, what do I get? Well, if you look at this, pretty much the only force applied to this is, well, weight is trying to take it down, mg, and the spring is trying to push it back up, and that spring force would be K delta, right? K multiplied by how much the spring is deformed. In this case, I called it delta. And there is no acceleration, so this is just nothing there. So from there, I'll get K delta, or we want to be more thorough, we can just say summation of forces in y direction is equal to 0. So what happens is that K delta is equal to mg. Let's keep that here. All right. Now, the next step that I will go and give some initial displacement or velocity to this. Some initial displacement. I'll pull it a little bit and let it go. So it starts oscillating. Now it oscillates, pay attention to this. It oscillates around the equilibrium point, right? If this is the equilibrium point right now, here is the equilibrium point for the new system, right? Delta amount below where it was. If I give some initial displacement or stretch it a little bit, see what happens. Well, it's a little, let me try to pull it straight. See what happens. It oscillates around the equilibrium point, which is here. So that's what I do. For next step, let's say I go there and let's look at the system now. So let's stretch it and let's say it's oscillating, and I'm going to continue these lines, this one and this one. We can do a little better, I guess. This one and this one. And this spring is going to stretch. And well, let's say the mass is here. So now I call the motion or displacement from equilibrium point X. Right? The same way I did for the spring and mass in horizontal direction. Right? Just in this case, the equilibrium point is different. So this is X, this is delta, right? This is K, the spring. Now let's write the equation of motion for this system now. This oscillating, vibrating system, which is not in a static equilibrium. Now it's oscillating, but it's oscillating around the equilibrium point, equilibrium position. So for the oscillating system, we get, well, let me draw a free body diagram here, M. Now, well, the gravity is still there, mg. What is pulling it down? Can someone tell me what is the force of the spring now? I'll wait. So the force of the spring is K multiplied by the amount the spring is stretched. How much the spring is stretched now?
The delta?
Well, delta plus X, right? Delta was when we were in equilibrium point. But now if we're going X amount further, now the spring force would be K delta plus X. And that is equal to acceleration. And I'm taking, I'm assuming the mass is going down. As I said before, always take well, this is assumption I make. So this is going down. Let's not get ahead of ourselves. Mx double dot. And when I write the equation, Ma, I take the direction of the motion that I assumed as positive direction. So this is positive. So I'll write it now. So this becomes minus K delta plus X plus Mg, is positive downward, is equal to Mx double dot. Now let's move things around. When I get Mx double dot, I will make, let's put it this way, plus Kx is equal to Mg minus K delta. All right, I just kept Mx double dot on this side, multiplied K by whatever I had in parentheses. So I get minus Kx, took it to the other side, it became plus Kx, and Mg and minus K delta on this side. Now look what I got here. Here, all right, let me use this. Here is Mg minus K delta. What is Mg minus K delta? We have it here, folks. This is Mg minus K delta. It's just 0. So what comes out of this is just pretty much Mx double dot plus Kx equal to 0. So interestingly, I got the same equation of motion, although the system was oscillating this way. So what is the conclusion here? This is important. Listen to this. The conclusion here is whenever the system starts oscillating from equilibrium position, for the rest of this course, again, important because whatever I say is a general conclusion. Whenever the system starts oscillating from its equilibrium position, we can safely ignore the effect of weight, okay, when we are using Newton's methods to derive the equation of motion. Okay. Because in this example, you will see they cancel each other out. Any example you write, even if for a mass on an inclined angle, on an inclined surface, you will, if you write down the equation of motions and show different components, including weight, you will get the same thing. Now, we got the equation of motion. What next? Well, what did we do when we were talking about pendulum? We found the system response, right? We solved this differential equation. So it seems like we have to solve this differential equation again, another differential equation, and find the system response. However, if you look at this, so equation of motion for spring mass becomes mx double dot plus kx is equal to 0. Let's compare that to what we had from before, equation of motion for a simple pendulum. Simple pendulum. What was that? L theta double dot plus G theta is equal to 0. Look what we got. We got the exact same differential equation, second order linear differential equation, which is homogeneous. Right side is 0. So good news, we don't have to solve this mx double dot plus ks equals to 0. We can just use whatever we had, everything we had pretty much from simple pendulum for this system now. And it happens over and over in vibrations. That's the whole idea of solving differential equations to find a system response for specific systems response. Because whatever system we have later on, you will see that we get to a point that once we derive the equation of motion, we realize that this equation of motion is similar to what we had from before, at least one of the systems we had from before. So let me write everything here. Let me do it this way. Let's go with simple pendulum, and spring mass. Let me see if I can do it in an organized way. I don't know how big of a table do I need. I'm gonna do this and do this. So start from the beginning. Equation of motion, all right? I have this table somewhere, so I wanna make sure that I cover everything. So equation of motion. For a simple pendulum, what did we get? We got L theta double dot plus G theta is equal to 0. For a spring mass, we got mx double dot plus kx is equal to 0. Look how we can just replace L with M and G with K, and pretty much whatever we had from before would be the same. Now, we can divide both sides. Do remember I convert that into a type of equation, or I rewrote this in a way that I could use natural frequency in the equation directly, or I could write it based on natural frequency. If you divide this by L, then we'll get L theta double dot plus omega n squared theta is equal to 0. Same thing here, x double dot plus omega n squared x is equal to 0, which this means that the natural frequency, I'll show that with NF. Natural frequency, well, for a simple pendulum, we define that as square root of G over L. Now, for a spring mass system, we define it as K over M. Omega n is equal to K over square root of K over M. Following the same procedure. Right? I'll move it a little bit this way. What else? Initial conditions. Initial conditions. In simple pendulum, well, we had theta naught and theta naught dot, right? Initial displacement, initial velocity. Now, for a spring mass system, we have x naught and x naught dot. Keep in mind the units, units are different. For a simple pendulum, initial displacement is in radians and initial velocity is radian per second. For a spring mass system, initial displacement is in meter or centimeter or millimeter, whatever unit you use for length. And the velocity would be meter per second, initial velocity. So, as you see, I'm just using whatever we have from before. I don't want to solve this differential equation again because I don't need to. System response. So if you solve this equation of motion and get the system response, remember the system response for a simple pendulum was theta t is equal to A sine omega nt plus phi. And for a spring mass system, well, same thing. I just replace theta with x. So I can find the position of this mass. How far is that from equilibrium point at any given moment using A sine omega nt plus phi. Now phi is a little different, A is a little different. We'll see we just replace again theta with x and theta dot with x naught dot. So I'm going to put amplitude. The amplitude would be, well, for a simple pendulum, we saw it was, let me write exactly the way I wrote before. It was, draw this, it was theta naught squared omega n squared plus theta naught dot squared divided by omega n. Now for a spring mass, well, it will be square root of x naught squared omega n squared plus x naught dot squared divided by omega n, right? So as long as you know the initial displacement and initial velocity of a spring mass system, you can find A. The last thing, I believe, is phase. So phase for a simple pendulum was tan inverse. Let me try to make it a little better. Was tan inverse theta naught omega n over theta naught dot, while for a spring mass system, it becomes tan inverse, pretty ugly tan. It becomes tan inverse x naught omega n over x naught dot. Hopefully I covered everything. So the same story about the spring mass system. Right? They are, as I said at the beginning, in nature, these two systems are pretty much the same because they have the same equation of motion. Any question about this, guys? Now I'm going to go over a couple of examples, but did it make sense what we used from before we had for simple pendulum, and how did we use it for a spring mass system in different configurations? No question at all. We are good. So you are, when you are given the system properties for a spring mass system, which in this case is a stiffness and a mass, and you're given the initial conditions, you can easily find the system response by finding the amplitude and phase. And if I tell you what is the velocity of that, well, whatever the system response is, take derivative with respect to time, you get the velocity. I tell you what is the acceleration of this system, well, take derivative with respect to time twice from the system response. Okay, let's take a look at a couple of examples then. We'll see. I'm hoping that this silence means everything was clear. Okay. Let's just start with something pretty straightforward. Let's say we have a spring mass system, a mass spring system. I might refer to it either spring mass or mass spring. Thank you, Cindy. Somebody confirmed that is following. Okay, so a spring mass system, has M, or the mass is 1 kilogram, K, or stiffness, is 2,500 Newton per meter. That's it. And the question is asking us to find the magnitude or the amplitude. Find the magnitude. Now, you might see magnitude and amplitude. They're pretty much the same. If there is any confusion, explain, but some textbooks refer to this magnitude, some textbooks refer to this amplitude. I personally prefer amplitude, but magnitude and phase, that's it. You know what? You need actually more information. If we have initial displacement as -2 millimeters and initial velocity as 100 millimeters per second. So we are given initial conditions and system properties, which is what we need we need to find the system response or anything that we want related to system. Now, where do I start? Well, let's see if I start from the end. I want to find magnitude, right, or amplitude. A is equal to square root of x naught squared omega n squared plus x naught dot squared divided by omega n, and phi is equal to tan inverse is 2 I'm asked to find. X naught omega n over x naught dot. Now, what do I need to find these? I have x naught and I have x naught dot. What is missing?
Omega n.
Omega n, right? I have to find the natural frequency. Exactly. Thank you. So let's go for omega n. Omega n, what was omega n for a spring mass system? Going back to this table, well, here is omega n. This is omega n, this column. For a spring mass system is a square root of k over m. I know k and I know m, so pretty much is a straightforward approach. K over m. So that would be square root of k is 2500 over m. I guess I got a little lazy here. I used very round numbers. So this becomes 50 radian per second. Keep in mind the unit for natural frequency does not change. The unit is the same. Even though we are dealing with a spring mass system, if you think about that plot, the sinusoidal plot, we are still looking at a sine function. So still the natural frequency is radian per second. Now we have natural frequency, so we can find A and phi, right? So A now becomes a square root. Well, x naught is minus 2. Did I convert that? I guess I just went with millimeter. So minus 2, not a good practice. You guys try to convert everything into SI system. Minus 2 squared, omega n is 50 squared, plus x naught dot squared, which is 100 squared, divided by omega n is 50. So this gives you A. And phi is tan inverse. X naught is minus 2 times omega n, which I got 50 divided by 100, and that also gives you phi. So A becomes, hopefully my calculations are right, 2.8284 millimeters, and phi becomes minus 100 divided by, did I make a mistake calculating phi? No, I guess that's correct. So this becomes tan inverse of minus 100 divided by 100. What is that? What is the value for this? What do we get for tan inverse minus 100 over 100? Anyone can tell me that. Just want to double check the equation.
Negative 45 degrees.
So what do we get for that?
Negative 45 degrees.
Negative 45 degrees, yes. So this becomes minus 45 degrees. Or if you're going to go positive way, just plus 180. So I guess it becomes 135 degrees. So, okay, hopefully that was a straightforward example. All right, we have system properties, we have initial conditions, just use that to find the system, amplitude and phase. Now, next example, let's make it a little more exciting. Let's go with this. So example, I'm telling you that we have a vibrating system, has the cohesion of motion, has the, I'm going to be lazy and put the OM, a cohesion of motion of 4 x double dot plus 16x is equal to 0. And what I'm asked is, what is the time period for this system? Time period for this system. So now I gave you the equation of motion already. How do we go from this? How do we use this information, this equation of motion, to find time period? Remember, time period was related to natural frequency. So first we have to find natural frequency.
So we do omega n is equal to square root k over m.
So what are our k and m?
K is equal to 16, m is equal to 4.
Exactly. So I just compared that with the equation of motion, right? If you go back and see the equation of motion here, we had mx double dot plus kx is equal to 0, and just use that. Or you can just, what I'm going to do, I'm going to convert that into the equation of motion written in the form of natural frequency, which is pretty much the same thing. So I take this and divide that by the coefficient of x double dot to get rid of that, to make it 1. So this becomes 4x is equal to 0. Now this is my omega n. Well, let me not use blue. I'll try hard in this course to be consistent with colors. Omega n squared, right? So if I do that, now from there, omega n squared becomes 4, meaning that omega n is 2 radian per second. Now what I want is time period. What was time period? Do you guys remember what was the relationship between time period and natural frequency?
Isn't it omega n is equal to 2 pi over t?
Exactly.
And t was our time period.
That's correct. So omega n, I'll go from there, 2 pi over t. So you can find t as 2 pi over omega n, meaning that time period would be 2 seconds. So that's pretty much it. That's what we're looking for. Hopefully that makes sense. Okay, next example. Did it make sense, guys? Hopefully that was straightforward and things just playing around with what we've learned. And I want to make sure that you're comfortable with the concepts and how things are related and how can you go from one to another. Now another example. Now in this one, I'm telling you that if a spring mass system let's say with m equal to 10 kilogram oscillates twice every second, what is the spring stiffness for this system? What is the spring stiffness for this system? Cindy, I'm not sure what that number is. You typed there. Did I make a mistake somewhere?
Oh no, sorry, that was my bad. I don't know what that was from. I guess.
Oh, okay, it's all good. Okay, what is the spring stiffness for this system? How do we do this? What I know is, I know what's the mass of the spring oscillating for this oscillating system. And I have given this information that it oscillates twice every second. Now, when a system oscillates twice in 1 second, what is its natural frequency? Right? Natural frequency was the number of, we define natural frequency, if you remember, and we used 2 units for that. One was radian per second, the other one was hertz. Does anyone remember what hertz was? Or definition of natural frequency in hertz?
Isn't a hertz a 1 over seconds?
But that's the unit 1 over seconds, exactly.
Yeah.
Dominic. But what was the definition of that? What is the frequency of this system now? Knowing the concept of frequency in hertz. If you
When
remember,
something is like moved or like it's left to like vibrate and then it just continues by itself, and we just let
well,
it.
so what I'm saying, what I'm told, that it takes 1 second for this system, right, to finish 2 cycles. Right? So let's say if it starts from here, or if I pull it down a little bit, it goes up, comes back 1 cycle, again it goes up and comes back 2nd cycle, right? And that takes 2 seconds. So if you remember, when I defined natural frequency in hertz, I said pretty much it means number of cycles per second. So here we are told that we have 2 cycles in 1 second. So easily, just pretty much we are given the natural frequency in hertz as 2 hertz, following the definition. Number of cycles per second. So now we know natural frequency is 2 hertz. So this should make your life much easier. How can we find the stiffness from here now, knowing that natural frequency in hertz is given? This is oscillating in a very weird way. So I know omega n for a spring mass system, right? I know that is square root of k over m. So somehow I have to find omega n. I'm given mass to be able to find the stiffness. Now, how do I find omega n from Fn? How do I find natural frequency in radian per second? 2 pi Fn. Yeah, exactly, Anton. Thank you. So omega n is equal to 2 pi Fn. So this means this would be 2 pi times 2, and this becomes 4 pi. So knowing that, well, k, if I don't make a mistake, would be m omega n squared, meaning that 10 times 4 pi squared. See if I have the number there. I just wrote it based on pi. So this becomes 160 pi, just multiply these, Newton per meter. That would be the stiffness of the spring for this system. Okay? Did that make sense, guys? Okay. Next example. I have a spring mass system. Keep in mind, a lot of what I say here can be kind of modified and be applied to a pendulum. Right? Just in this case, we have just a spring mass system. But I'm going to repeat myself that they are the same in nature. If you think about it, L plays the role of mass in a pendulum, and G plays the role of stiffness. Now, this problem tells me the spring mass system, spring mass system. I'm going to go over these examples just to make sure that you're comfortable with the equations and you know how to pretty much work with them. Spring mass system, is excited from its equilibrium position, from its equilibrium position with initial velocity, with an initial velocity of 1 meter per second. What I'm asked to do is I want to find the system response if find the system response if M is 10 kilogram, 10 kg, and K, stiffness for the spring, is 1,000 Newton per meter. Pretty straightforward. If you go back to the table there, when I was talking about system response for a spring mass system, well, A sine omega nt plus phi. Well, to find this, we have to find A, omega n, and phi, and pretty much plug them back into the general form of the system response. So that's what I'm going to do here. I'm going to go with A. Let's start with, well, let me follow what I did before. So omega n is just thing to calculate. Square root of K over M. Square root of K, which is 1,000, divided by M, which is 10, comes the square root of 100, I believe, and that would be 10 radian per second. I guess I chose the numbers very wisely. The second thing I need is the amplitude, A, would be square root of, I don't know why I'm putting it very close to the previous line, x naught squared omega n squared plus x naught dot squared divided by omega n. You plug in the numbers. You're just given the initial velocity. Maybe I should add something along this, that initial, well, you know what? Actually, it's already given. When you look at the problem, it says it's excited from its equilibrium position. So there is no initial, no, it can be vague. So let me just add it. Initial displacement is 0. Because that can mean different things when you say the motion starts from equilibrium position. Okay, so x naught squared, well, 0 squared, obviously, times 10 squared plus x naught dot, which is 1 squared divided by 10, this becomes 0.1. You can find phi, right? I don't think I'm going to run out of space. So phi is equal to tan inverse was x naught omega n over x naught dot. Now this becomes tan inverse. Well, x naught is 0 times omega n is 10 divided by x naught dot, which is 1. This gives us what? What do we get for angle or phase? What is the tan inverse of 0?
0.
0. Technically, just want to let you know, guys, it can be either 0 if you look at the unit circle. I'm going to try to draw it here. If you look at the unit circle, for some reason, totally away from the center. It can be 0, so this is sine, or the other way around. This is cosine, the other one is sine. This is cosine, and this is sine. And this unit circle to radius is 1. Tan is, what is tan? Tan function is tan of, let's say phi is equal to sine phi over cosine phi. So technically, when you get tan equals to 0, wherever sine is 0, tan is 0, which means you can either be here or here. So the angle could be 0 or pi when the argument for tan inverse is 0. Now, how do we figure out we are on 0 or we are on pi? Can someone tell me this? Where are we? Well, we know we are looking at tan inverse of 0, but tan is sine over cosine. So wherever sine is 0, tan could be 0, meaning that we could be on 0 degree, we could be on pi degree, pi, right? In one, at least the first round. How do we decide which one is the right number? Can anyone tell me that? How do you know that the value is not pi? Any thought on that?
Is it because of like the direction, like negative to the left and positive to the right, or no?
Yeah, exactly. You're on the right path. So if you look at what the cosine value is on these points, right? So cosine of 0 is 1. Cosine of pi is -1. Look, what do we have in our denominator? In our denominator, we have 1. Meaning that cosine of that angle, whatever angle is 1. And sine of that angle is 0. So we can figure out that we are on 0. If this number was -1, which is not here, if it was -1, you would still have tan inverse of 0. But now your phase angle would have been pi. Hopefully it makes sense to you guys. So we have omega n, we have a, we have phi. Xt, or the system response, would be 0.1 sine 10t plus, well, 0. So pretty much 0.1 sine 10t. That will describe this motion. Now, what if I tell you what is the velocity for this system? What if I tell you what is x dot of t, or what is the acceleration of this system? You just easily take derivative with respect to time, right? If I take one derivative, 0.1 sine 10t, 10 comes out, 10 times 0.1 would be just 1, so it becomes sine 10t. Sorry, cosine 10t, obviously. Sine becomes cosine. So this is velocity. If the unit for this is meter, the unit for this would be meter per second. The acceleration will take another derivative. It would be -10 sine 10t. This would be meter per second squared. If you think about the plot we had for, let me just make sure that we had for a pendulum, right? Sine plot, exact same thing with the same parameters, just use the same plot. The beginning is x naught, initial displacement, the slope of the line is x naught dot at the beginning, and everywhere there would be x naught, it would be x dot as the velocity. The distance between two peaks is time period. So if I give you the plot of a vibrating system, looking at where the initial position is, the distance between two peaks, you should be able to estimate a lot of system parameters. Another example. Now in this example, let's see what I got. Very similar to well, this is a little different. So in this case, I want to give you the system response. So let's say a vibrating system follows motion described by xt is equal to 1.5 sine 0.16t plus pi over 4. Right? So I tell you what is the system response for this, whatever vibrating system is. Now, I'm asking you to find the initial displacement, find the initial displacement, or maybe just follow that, and velocity, initial displacement and initial velocity for this system, So how do I do that? Just make sure that. Any thought on this? Oh, I'm going to keep this steady.
You could plug in 0 for t,
You can plug in 0 for t.
and then we take the derivative, and then we can get the velocity.
Yes, right. That should give me what I want. Let's see. So at t equals to 0, right, x naught, which is displacement at t equals to 0, would be sine 0. So that becomes 1.5 sine pi over 4. Let me see if I have the number there. Well, it's actually sine pi over 4 it becomes 1.5 times square root of 2 over 2. I actually don't have this number, but whatever comes out of this, let's use the unit meter for this. So we can say this is in meter. Let me see if I have my calculator. We can just calculate that right now. So 1.5 times square root of 2 divided by 2. This gives me, let me see, 1.5 times sine pi over 4. Yeah, so this gives me, where is that? So I can write in front of it, 1.06 meter. That's the initial displacement. Right? How about for initial velocity? Well, you just take derivative with respect to time, right? You just find x dot t. I'll leave it to you to do this. X dot t, and then put t equals to 0. From there, you will get x dot naught as whatever becomes meter per second. Does that make sense, guys? Because that describes the motion of the system. So pretty much whatever you get from this should work, as we say. Okay, any question, folks? We're good? Nothing confusing? So what I wanted to do today was, let me just recap what we did. I introduced a new system, vibrating system, spring mass system. We derived the equation of motion for that system, and we realized that the equation of motion is exactly the same as pendulum in terms of its form. It's a second order homogeneous linear equation of motion. Now, from there, we use whatever we found for a pendulum, right? System response, natural frequency, time period, initial conditions, whether velocity or displacement, anything we had from before. So we did not need to solve the equation of motion anymore. And that happens a lot during the course of this, during this course. Now, And then I went over a couple of examples, and we saw how can we actually use those equations to describe the motion and figure out how this system works. Now, there's one last thing I want to talk about, that it's what happens if we have more than one spring. What if we have a mass connected to one end, let's say, or the ceiling or some angle, but there is more than one spring? You have one spring on one side, the other one at the other side. So let's go with spring configurations. Now, the analogy is very similar to what we have in circuits, actually, when you're dealing with circuit boards, electronics. So we say springs can be in series or in parallel. I don't get into detail of how can we derive these, but what I'm going to give you as the equivalent, as they call it, for these springs or these configurations. But springs can be either in series or in parallel. So if we have spring in series, what do I mean by series? So if I have a mass right here, and that mass is connected to some wall, not just by one spring, this is K1, but by more than one spring. In this case, 3. But in general sense, there can be more. So what happens is that we say, well, this system, a mass with a series of springs connecting to a support, we can replace this with just this simple system, spring and mass system, and I call this a spring equivalent, K equivalent, meaning that there's an equivalent stiffness. So what is the value of this K equivalent? That's all we need, because mass is the same. So for spring in series, K equivalent is pretty much the summation of K values. So K equivalent, no matter how many K's springs you have, as long as they are in series, I'll tell you in a minute what series is, from 1 to n. For n number of springs in series, K equivalent is pretty much just the summation of K's. Now, when do we, this is very important, keep that in mind. When do we say springs are in parallel? If the springs have equal displacement, the absolute displacement, not the, we don't care about the sign. If the springs have equal absolute displacement during the motion, they are in parallel. If you think about this here, right, if this one moves X amount, right, all these springs here, they stretch X amount. So they stretch exactly the same amount. And so they are in parallel. Now, when do we have springs in parallel? Well, one case is this. It's a very obvious one. Another case is, as I said, as long as the amount of displacement is the same, they are in parallel. So another case would be this case. If we have a spring, if we have one spring on this side, and we have the mass and another spring on that side. Right? This is K1, this is K2. See what happens. If this one moves X amount, well, the spring on this side is going to be stretched X amount. The spring on this side is going to be compressed X amount, assuming that the motion starts from equilibrium position and both the springs are undeformed. Right? So these two springs are also in parallel. So K equivalent, this system is an equivalent to a system like this, and this is K equivalent. Oh, no friction. So, And for this system also K equivalent is K1 plus K2. Right? So this is the situation where springs are in series. Now, the other case, as I said, very similar to analogy we use for circuit board when we're analyzing circuit boards. Springs in parallel. Sorry, I was totally off here. I'm glad I figured that out. This is not springs in series. I apologize for that. This is springs in parallel. Right? This is springs in, for some reason I can't erase this, so I'm going to scratch that. Springs in parallel. I apologize. Whatever I said was for springs in parallel. Springs in parallel have the same displacement. Now spring in series. Again, sorry for the confusion. So springs in parallel, as long as the springs have the same amount of displacement, amplitude or amount or magnitude of displacement, they are in series. They are in parallel. So we just sum them up, sum the stiffness up, and get an equivalent system. They call these equivalent systems. This is an equivalent system just because it's equivalent to what the system we had, but it's simplified. Now, spring in series, as you can guess, well, if I have a situation like this, if I have one spring here, K1, another spring there, K2, another spring there, K3, and just a series of a spring all connected to a mass here. Let's call it Kn. Now, these are springs in series. The equivalent of this would be a system like this, K equivalent with M. Now the equivalent for this, well, let me just put this. Now this K equivalent is 1 over, correct that, 1 over K1 plus 1 over K2 all the way to 1 over Kn. So in general sense, K equivalent for springs that are in series would be 1 over summation of a stiffness 1 over Ki, I from 1 to n. If you have n number of springs, they are in series, you can just rewrite the system and change it into a very simple system like this. This one. By replacing all of the springs with one spring, as long as that spring has that stiffness. So as you can see, you might infer this, you might get this from this general sense from these systems, that if you have a series of, you have springs connected together in parallel, you're actually increasing the stiffness of the system. Think about it here, right? This equation. You're adding more stiffness to your system. If you have springs in series, that doesn't work the same way. So a lot of time when we want to increase the stiffness of a system, right, we can just easily add, well, this is a simple spring mass system, but you'll see later on, in general sense, we add more stiffness in a way that the stiffness is in parallel with the previous stiffness. So we can actually manipulate the natural frequency of the system, because natural frequency is square root of K over M. Right? Now, for this system, just want to mention that, for this system, then natural frequency becomes what? Natural frequency for this system then becomes square root of K equivalent over M, right? Because now that's the stiffness of the system. Or for this system, natural frequency also becomes K equivalent over M. Right? I'll talk about K equivalent and even equivalent of mass when we'll start looking at systems with different configurations. But I just wanted you to know the spring configurations because you'll see springs in different ways connected to a system. Okay, I'm just going to stop here. Any questions, guys? So just want to mention that whatever example with the spring mass system, if you have multiple springs connecting a mass, just add those stiffness values up and it becomes a simple spring mass system. And as long as you use K equivalent as the value for K, whatever we found in these tables, in that table, right, as long as you replace K with K equivalent, you can just follow exactly the same thing. Right? Keep in mind, natural frequency should be found using K equivalent. And from there, everything else changes for a system with multiple springs. Any question, guys? Anything you have in mind? I just want to go quickly. Let me